Welcome to our multiprocessor system simulation project. This work represents a simplified yet realistic model of how modern processors cooperate to execute tasks in parallel while maintaining coherence in shared memory. Our goal was to simulate in C++ a small multiprocessor system that includes processing elements, private caches, a snooping interconnect, and a main memory, all synchronized under the MESI coherence protocol. Let's start with the theoretical foundation. In a shared memory multiprocessor, multiple processors or cores need to access the same memory space. Each processor has a private cache that keeps recently used data, so it can work faster without constantly reading from the memory. However, when different processors modify the same data, inconsistencies can occur. To solve this, systems use cache coherence protocols, in our case, the MESI protocol, which ensures that all caches maintain a consistent view of shared data. All communication happens through a shared snooping bus. Each cache listens to this bus, or snoops, to detect when other processors read or write shared data. This allows them to update or invalidate their copies when necessary. It's a simple but effective approach for systems with few processors. In our implementation, each processing element, or PE, acts as a simplified processor core. It fetches instructions from memory, executes arithmetic operations, and interacts with its private cache. Each PE runs on its own thread, simulating parallel execution. The PE also includes a small register file in an instruction counter, just like a real CPU pipeline, but simplified for functional modeling. Each cache stores 64 data words and implements the MESI protocol, modified, exclusive, shared, and invalid. When a PE reads data, it first checks if it's already stored in its cache. If it's not, it triggers a bus read. Other caches then snoop this operation and respond according to their states. For example, if one cache holds the block in the modified state, it must write it back to memory before another processor can read it. This ensures global coherence, even though each processor operates independently. The interconnect in our simulator is a shared snooping bus. It connects all caches in the main memory. Every memory request, read, write, or upgrade is broadcast to all connected caches. The interconnect ensures that all caches are aware of every operation, maintaining the global state of the system. In contrast to directory-based systems, this broadcast-based approach is simpler and ideal for small-scale processors, like our 4-core model. The main memory module stores the shared data. This is divided into logical segments, code, data, and stack. Each one with a strict 8-byte alignment. The simulator enforces access validation for every read and write. To emulate the behavior of a real processor's memory controller, all operations are 64-bit double words, ensuring consistency between the caches and the main memory. To make our system programmable, we designed a custom instruction set architecture, or ISA. It includes operations such as load, store, fmul, fadd, inc, dec, and gnz. The ISA loader reads the .isa file, a small assembly-like program, and translates each instruction into a 64-bit encoding. Then it loads this binary program into the code segment of memory. Our test program implements the dot product algorithm. It multiplies pairs of elements from two arrays and accumulates the total. This example demonstrates both computation and memory coherence, since multiple processors can work in shared data simultaneously. Once initialized, the orchestrator sets up the memory, attaches all caches to the interconnect, and launches the 4 processing elements in parallel. During execution, the terminal output displays memory transactions, cache hits and misses, and snooping events, providing insights into how coherence is maintained step by step. Finally, the resulting value of the dot product is stored back in memory, confirming the correct synchronized behavior of the system. This project demonstrates how hardware concepts like coherence, communication, and synchronization can be modeled in software, bridging the gap between computer architecture theory and practical implementation.